In section 2.3, we're continuing on with quadratics. We're using some of the same business ideas we had in the past, like a break-even point or finding a maximum value. Suppose the total cost function is given by 21,000 plus 40x plus 0.2x squared, and then we're also given a total revenue function. Find the break-even points. So remember that break-even can be thought of in two different ways. First one is that the profit is equal to 0, and the second way is that cost is equal to the revenue. Mathematically, those two equations say the same thing. The one that you'll use depends on the information that you have. Since we are given a cost function and a revenue function, I will use the cost equals revenue approach. So cost equals revenue. I now have a quadratic equation. So to solve it, I need to set one of the sides equal to 0. So I will move the 0.8x squared over to the other side and subtract 410x from both sides. Now I've got 1 whole x squared minus 370x and plus 21,000 equals 0. And I want to solve for it. You could try to factor. If you're really good with your 21,000 times tables, that would work. Or you can just go with the quadratic formula. X equals the opposite of b, which is positive 370, plus or minus square root of 370 squared, minus 4 times a, which is 1, times c, which is 21,000, all over 2 times a. That's 370 plus or minus 370 squared is 136,900. And then minus 4 times 21,000 is 84,000, all over 2. 370 plus or minus, this square root will turn out to be 230, all over 2. Now I've got x is either 370 plus 230 over 2, or x is 370, take away 230 over 2. First one, 370, that's 600 over 2, that's 300. Or 370 minus 230, it's 140 over 2, which is 70. Those are both perfectly fine numbers for x. Notice that x is the number of units in this problem, and you could have positive 70 or positive 300. So you enter it into WebAssign and just put a comma in between them. You have 2 break-even points. Which begs the question, is it possible to break even twice? How can you have 2 different break-even points, and especially 2 such different break-even points? And the answer is yes, you can. So if either your cost or your revenue is quadratic, then your profit will be quadratic. And when your profit is quadratic, it will be a parabola. And the break-even points are these. So the first time you break even, you went from a loss to a profit. That's a happy break-even point. And over here at 300 units, you stop having a positive profit and begin to have a negative profit. So you go from a profit to a loss. So profitability is between 70 and 300 units. Less than 70, you have a loss, and more than 300, you have a loss. Next, suppose that we're given a profit function, and we're asked to find the break-even points. Because we're dealing with a quadratic function, we could have 2 viable break-even points. And because we are given a profit function, I will use the logic that says break-even happens when profit equals 0. So I take my profit function and set it equal to 0 and solve. Okay, if you have a negative in front of your x squared, it just becomes a little bit trickier to solve. I'm going to exercise my right to multiply an equation by a -1 on both sides if I want to. That would be a positive x squared. I'm also going to rewrite it in standard form. So positive x squared, negative 145x, and positive 3,000 equals still 0 on the other side. To solve, x is the opposite of negative 145, so positive 145 plus or minus square root of 145 squared minus 4 times a, which is 1, times c, 3,000, all over 2 times a, which is 1. 145 plus or minus, simplify under the square root, I get 21,025 minus 12,000. 145 plus or minus 95 over 2. So I have two values for x. X is either 145 plus 95 over 2, or x is 145 take away 95 over 2. For the first one, I get 240 over 2, which is 120 units. For the second one, I have 50 over 2, which is 25. So I have two values for x. In WebAssign, you'll enter them separated with a comma, 25 and also 120. At 25, you break even in a good way. You go from a loss to a profit. And at 120, you break even in a bad way. You go from a profit to a loss. In the next problem, we are asked to maximize the revenue. So we're not trying to break even anymore. We're trying to maximize. The problem is that we want to maximize the revenue, but we were not given a revenue function. All we were given is that revenue is price times quantity. What we were given was a demand function. So I want you to remember from your microeconomics that in a demand function, you're talking about price interrelating with quantity. So your demand function always has only two variables. One of them represents price, the other represents quantity. Since we're asked to maximize the revenue, the first thing we need to do is build a revenue function. But price, I know, equals 185 minus 0.2x. And so I will substitute that expression in for price. And then times quantity. Quantity is x. Now I can distribute the x through, and I have built a revenue function that is a function of a single letter x. So given a revenue function, how do you find the maximum? As you recall from the last section, it's at the vertex. And how do you find the vertex? You find the x-coordinate first. It's at negative b over 2 times a. For this problem, that's negative b is 185. It's the coefficient in front of the x. Over 2 times a is the coefficient on the x squared term. Negative 185 over negative 0.4 gives me 462.5. Okay, 462.5 what? Well, that was an x. So it's whatever x represented, and x was units. However, if I put in 462.5 and I check it, it's wrong. And that's because they didn't want the number of units to maximize the revenue. They want the price to maximize the revenue. So if I have the units, how do I find the price? Well, I need to find a function that will take x's, units, and convert them into p's, price. And that's this one. It's the demand function. So go to the demand function, 185 minus 0.2 times, fill in your number of units that you just found, and work it out. I got 92.5, and now 92.5 what? Well, that's price, so that's dollars, and that's selling price per unit. Next, we need to talk about some basic business definitions regarding the total cost function. We've got fixed cost, variable cost, and total cost. When I ask students what are fixed costs, they usually say those are the costs that you have no matter what. And I say, what do you mean no matter what? They say, well, no matter what you do, no matter how many items you produce, you still have those fixed costs. That's true. So for us, let's say your fixed costs were $3,000. You have $3,000 of cost even if you have made nothing. So for purposes of a math class, when x is 0 units, cost is 3,000. And then if you actually produce something, your costs go up from there. That $3,000 covers rent, insurance, all of the overhead that goes into the production. So even though you haven't produced anything, you still have cost. And then when you start to produce, you've got variable costs, and those are per unit costs. So let's say your variable costs were 57 cents, and that's per item. Then your total cost function would be, I have $3,000 of cost, plus I will have 57 cents per item. That will be 0.57. and then per x. Okay, now nobody would say my total cost function is 3,000 plus 0.57 plus 57 cents, because it's not just 57 cents, it's 57 cents per item, so you'd have to multiply it by another x. Let's try this again. What if your fixed costs were $5,200, and now your variable costs are going to change depending on how many you make. So your per unit cost, let's have it be 2/3 x plus 200. So the cost per unit could change depending on how many units you make. That actually is more realistic than saying you always have 57 cents no matter how many you make. Cost equals fixed costs plus variable costs, but what I've written so far is equivalent to my second statement. That doesn't make any sense. It has to be variable cost times by another x. So I need variable cost, that's per unit for 1 unit, times by the number of units. So my cost function will be 5,200 plus, distribute the x through, 2/3 x squared plus 200x. Let's just try it again. $400 of fixed costs, 2x plus 5 of variable cost, and that's per unit. Then my total cost function would be fixed costs plus the cost per unit times the number of units. A lot of students say, well, how come I have to multiply by this other x because I've already got an x in it? Well, it's not the fact that you've already got an x in it, it's that you need variable cost per unit times the number of units. 400 plus 2x squared plus 5x. Okay, let's look at WebAssign. Suppose a company has fixed costs of $300, variable costs per unit of, and then there's a formula, so those are changing depending on how many units you make. X is the total number of units, and the selling price is given. So you have fixed costs, variable costs, and selling price, and they want to find the break-even point. Okay, the break-even point is either revenue equals cost, or it's profit equals 0. Well, I don't have a revenue and a cost function, and I don't have a profit function. So either way, I'm going to have to build the functions. I'm going to go with revenue equals cost. Okay, so first, revenue is price times quantity. That's price times quantity. And I know that price is given. There's my selling price. So I will substitute in 1,600 minus 1/4 x, price, times quantity. 1,600x minus 1/4 x squared. Hold on to that. Now I need to build the cost function. Cost function is fixed costs plus variable costs. Fixed costs is 300. Okay, now then on the variable cost, the 3/4 x plus 1560 is per unit. So to make that my total variable costs, I take per unit cost and I multiply it by the number of units. That gives me 300 plus, distribute the x through, 3/4 x squared plus 1560x. I have my revenue function that I built. I set it equal to the cost function that I built. And not surprisingly, in this chapter, I'm looking at a quadratic equation. So I need to set it equal to 0. I will choose to move the terms on from the left side to the right side. So that's 1,600x and add a 1/4 x squared. Now I've got 0 equals 300 plus 3/4 plus 1/4 is 1 whole x squared. Thank you, WebAssign. And then negative 1,600 and positive 1560 make negative 40x. Let me just rearrange this. Positive x squared minus 40x plus 300 is 0. These numbers are small enough you might be able to just go ahead and factor it. If not, you can put it into the quadratic formula. I'm going to factor it because I think it's going to be 30 and 10. That will make my 300. Both signs would have to be negative to get a negative 40 in the middle, and I have x's in front to get the x squared. FOIL that out, check it. but I think we got it. Then either x minus 30 has to be 0, so x would be 30, or x minus 10 would have to be 0, so x would be 10. I have 2 break-even points, and it says enter your answers as a comma-separated list, 10 and 30. Okay, maximum revenue is a totally different question than break-even points. It happens at a different number of units. Break-even points are when I have 0 profit, and here I want to have the largest possible revenue. My revenue function, to find the maximum, I find the vertex, and that happens at negative b over 2 times a, which is negative. B is the x coefficient, 1600, over 2 times a, which is negative 1/4. Negative 1600 over negative 1/2 makes 3200. That's 3200 units. Okay, now, is that what they wanted? No, they want the revenue amount. They don't want the number of units. They want the dollars of revenue. Well, so far I only know the x value. To find the revenue, I would take this x value and plug it in. So 1600, insert 3200 for your units, minus 1/4 times insert 3200, and square it. And when I clean that all up, I have 2.56 million dollars of revenue. That's enough to make you think you chose the right major. Part C, form the profit function. Okay, profit is revenue takeaway cost. My revenue function was 1600x minus 1/4 x squared. Takeaway, my cost function was, now be careful that you need to subtract the entire cost function, so you need to put parentheses around this, and that negative is going to have to distribute through in the next step. So my profit function, 1600x, negative 1/4 x squared, negative 300, negative 3/4 x squared, negative 1560 x. Combine it to get negative 1/4 and negative 3/4 is a negative 1. Thank you, WebAssign. 1600 minus 1560 is a positive 40, and then minus 300. Find the maximum profit. Okay. To maximize the profit, find the vertex. To find the vertex, I have x is negative b over 2 times a using the profit function values. So negative b over 2 times a, which is negative 1, gives me 20, but that's an x, so that's 20 units. They want the dollars of profit. To get the profit, I take my x value and I plug it back into the profit function. Negative 20 squared, 40 times 20 minus 300. Negative 400 plus 800 minus 300 is 100. The best profit I can ever get from this setup is $100. Okay, now let's think back just a minute. Remember when things were looking really good and I had this maximum revenue that was in the millions? $2.56 million of revenue? Well, it turns out that these costs must be skyrocketing because the most profit I can ever get will be $100. And my maximum profit happened when I had made and sold 20 units compared to my maximum revenue was at 3,200 units. So the lesson is if you only ever focus on revenue and you don't keep costs in control, you're going to go out of business because this is very, very different production levels. You need to focus on the bottom line, which is the profit. And then last, what price will maximize the profit? So I want to go to where did the maximum profit happen? At 20. So what was the price? And they mean selling price when X is 20 units. Well, I need to figure out how I would find the price if what I know is the number of units. And I erased it. So let's go to your problem. Fixed costs of 300, variable costs, X is the total, there it is. Suppose the selling price of the product is selling price 1600 minus 1/4 X. Maximum happens on the profit when X is 20, so I'll fill that in. 1600 minus 1/4 of 20 is 5. 1595, that's $1,595 per item, and that's your selling price that you should set. Okay, things just got really serious. In this single problem, we had fixed costs, we had variable per unit cost, we had a selling price. That's what they gave us to start off with. We built a total cost function. We built a revenue function. We built a profit function, and then we maximized the revenue, we maximized the profit. 1, 2, 3, 4, 5, 6, and then number of units was 7. That's 7 different variables, 7 different formulas and equations to keep track of in a single problem. So you've got to get organized, and you need to realize which piece of the problem you've found. So just because you've solved it and you've got an X answer doesn't mean you're done. You have to figure out what they want from there. Next, we'll look at number 6 in WebAssign, which gives a supply function and a demand function, and it asks 2 questions. First is to graph, and then the second is to find market equilibrium. The Watch It uses a graphing calculator. In our course, we don't get to use a graphing calculator, and you don't need one, so I'll show you how you do this without it. We're going to do part B first. To find the market equilibrium, equilibrium happens when supply is equal to demand. Insert my supply function, which is 1/4 q squared plus 12, has to equal my demand function, which is 72 minus 2q minus 3q squared. Not surprisingly, I'm looking at quadratics. So to solve this, I need one side set equal to 0. I will add 3q squared, I'll add 2q, and I'll subtract 72. Then I have 3 and 1/4 q squared. Let's make that 3.25 q squared plus 2q and minus 60. Set that equal to 0 and solve it. I'll use the quadratic formula, and the quadratic formula solves for the variable that has the squared on it. So this would be a q equals negative b, negative 2 plus or minus the square root of b squared minus 4 times a is 3.25 times c is negative 60 all over 2 times a, which is 3.25. This simplifies to negative 2 plus or minus square root of 784 over 6.5, negative 2 plus or minus 28 over 6.5. Okay, q is either negative 2 plus 28 over 6.5, which is 26 over 6.5, which is 4, or q is negative 2 minus 28 over 6.5, which is negative 30 over 6.5, which is negative 4.6, and then some other decimal places. In the context of this problem, q is the number of units that are being produced, and I can't produce a negative number of units, so this answer gets thrown out in the context of this problem. I only have one value for the quantity, which is 4. This was at equilibrium. Quantity is 4, then I need to know what was the price. To find the price, take q and plug it back into either the supply or the demand, whichever one you prefer. The supply looks shorter, I'll do that one. 1/4 times, plug in 4 for q squared, plus 12, I get 16. So my equilibrium happens when q is 4 units and the price is $16. Okay, I found market equilibrium. That's units and price. And now to graph, they give me choices. And I just have to narrow down from among the choices, and we can do this pretty quickly. And again, you do not need a graphing calculator in order to do this. Supply. Supply is a squared positive. Supply will be an upward opening parabola. Demand, the squared variable, is negative. So demand has to be a downward opening, supply has to be upward opening, and the equilibrium has to be at 416. First option, demand, downward opening parabola, yes. Supply, upward opening parabola, yes. Equilibrium at 416, yes. It looks like that's my answer. Just to compare, on the second one, supply has to be an upward opening parabola. It's not that one then. Next one is supply upward opening, no. Last one, supply upward opening, yes. Demand downward parabola, yes. Is the equilibrium point at 416? No. Okay, so again, I didn't have to have a fancy graphing calculator. All I needed to know was that supply was a parabola that opened up, demand was a parabola that opened down, and I had to find the market equilibrium, which wasn't hard. Let's look at the smokestack problem again. This is cost C of removing P% of the particulate pollution from the smokestacks of an industrial plant is given by. Very similar to a problem that we had in chapter 1. Is the function C of P undefined at any P value? So undefined means the denominator is 0. So I look at the denominator. Could 100 minus P ever turn out to be 0? Yes. If P took on the value of 100, then the denominator would be 0. So I cannot allow P to be 100. Is it defined? If so, at what value? At 100. What is the domain as given by the equation? So this is what I call a mathematical domain. It's not talking about what makes sense in the problem. It's just saying mathematically, the only restriction I have is that P cannot equal 100. So if you took a number line, and here's 100, and to begin with, you say every possible value of X is under consideration. But then from mathematically in the context of the problem, we know that 100 cannot happen. So here's what my graph looks like. This gives me two intervals. For the first interval, the leftmost endpoint is negative infinity, as far as you want to go to the left, and the rightmost endpoint is 100. And then my second interval starts at 100, and it goes as far as you want to go to the right, which is infinity. You combine those together with a union, and that's the mathematical domain. So that would be negative infinity to 100, union 100 to infinity. Let me show you how to type that in WebAssign. Okay, I need a parenthesis, and then I need a negative infinity. For infinity, you can come over here under symbols, and there it is. Now, I don't like to use a mouse a whole lot, but to 100, close parenthesis, which was already there. And then union, I need that fancy U sign. If you look at operations, no, sets. There it is, sets and union. And now I need my second set of parentheses. Starting at 100, going up to positive infinity, go back to symbols, get infinity. However, there are keyboard shortcuts. Parenthesis, negative. WebAssign, if you just type in infinity, we'll put the symbol in for you to 100. And then union, you could just type in the word union. There it is, 100 to infinity. And then what is the domain in the context of the application? So this is the common sense domain. So this goes back to what we were talking about in one of the last chapters. P can't be negative, so P has to stay positive. It would be okay to have a percent pollution of 0. That means you didn't remove any. That's okay. And the percent has to stay less than 100 because you can't remove 100%, or because you can't remove 150% or 230% of the pollution. You can only stay between 0 and 100. So in interval notation, the smallest I could have is 0%, and the largest I could have is as close as you can get to 100%, but I can't actually use 100 because the math won't allow it. One more mathematical concept that comes up in this section is piecewise defined functions. I think you'll remember seeing the big function with this bracket on it, and then somewhere in your past math classes you've probably seen this. This notation is somewhat confusing. Here's what's going on. You start with an x value, and then you put it into a function and you want it to build a y value. Well, this function has two completely different ways of determining how to build the y value. If the x that you give it is less than 1, then the y value will be built from x squared plus 4x. But if the x value is greater than or equal to 1, the y will be built from 2x plus 7. So it's an either or. The x value you input either gets sent up to the first branch on this condition that x is less than 1, or it gets sent down to the second branch, the bottom branch, on the condition that x is greater than 1. So if I want to find f of 4, the first thing is to figure out which branch. So x is equal to 4. 4 is larger than 1, so the function will send that to the second branch and figure out the value by plugging 4 into 2x plus 7, which will give you an answer of 15. But to find f of 0, take the value of 0, that's your x. You figure out which condition it meets. It meets the top condition, so it plugs it into the top branch, 0 squared plus 4 times 0, and you get 0. What's important to remember are that these two equations represent y values, and you do one or the other, not both. If we want to find the monthly charge in dollars for x kilowatt hours, the monthly charge depends on how many kilowatt hours we use. So between 0 and 35 kilowatt hours, this first formula is how you would figure out your total cost. But if you use between 750 and 1500 kilowatt hours, you'll use a completely different equation to find your cost. So find the monthly charges for 35 kilowatt hours. The first is to determine which one of these conditions is met. It meets the equals 35 condition, so I'm going to plug that into the top and find that my cost will be $7.52 plus 0.1079 times plug in 35 for x. That's a total monthly charge of $11.2965. Rounded would be $11.30. But for 38 kilowatt hours, that's going to move us to the second branch of this function. So to find the cost, I would take 19.22 plus 0.1079 times plug in 38. So you first decide which branch of the function your x condition meets, and then you plug it in to determine your monthly charge. Okay, I think that's it. This tax question, I'm going to have you watch the Canvas videos on that, and I will see you in class.